What's going on, people? Welcome back to Respiratory Shock Therapy. I'm Andrew Sanders, and this is episode 2.
I don't think she's breathing.
In today's episode, we're going to talk about physical principles of respiratory care. Basically everything that Ray's been teaching us so far, and he still has a ways to go on this first PowerPoint, and I'm not going to go past what he's taught us so far. So this is going to be a multi-part series. So, welcome to part 1. Let's get started. We talked about states of matter. There's solid, liquid, gas, and each one has its own little quirks. In solids, the position of atoms or molecules are essentially fixed. They can't really move around. And they have a strong mutual attraction called van der Waals forces. That's how solids keep their shape, so they don't conform to their surroundings like liquids and gases do. They're also hard to compress. Liquids, on the other hand, also have strong mutually attractive forces, but it doesn't affect their motion. So the forces create surface tension and viscosity, but the molecules are allowed to flow and conform to the shape of their containers. And gases have very weak attraction forces, and they have unrestricted movement. Gases are easily compressed and expanded, and they flow like liquid and conform to the shape of their containers. The next 3 things I want to talk about are potential energy, kinetic energy, and the first law of thermodynamics. So potential energy is the energy of position, kinetic energy is the energy of motion, and the first law of thermodynamics says energy can neither be created nor destroyed, only transformed in nature. So in order to visualize this, let's look at what happens when someone shoots an arrow across a field. So drawing the string back on the bow creates potential energy. Releasing the arrow converts it to kinetic energy. So eventually, the arrow will slow down and hit the ground. But where did the energy go? We just learned that energy can't be created nor destroyed, so we know the energy must have gone somewhere. So as the arrow was moving across the field, a lot of the energy was actually being released as heat, because there's friction created between the particles in the atmosphere, in the air, and the arrow. So they're actually like rubbing against each other, and it's creating resistance for the arrow. And this is more obvious when we look at a much larger, faster object flying through the atmosphere, like a meteorite. And then we can really get an idea of how much energy is being released through friction. Alright, so now let's talk about heat transfer. When 2 objects exist at different temperatures, heat will move from a hotter object to a cooler object. And there's 4 different types of heat transfer that we talk about: conduction, convection, radiation, and then evaporation and condensation. So, let's talk about conduction. Conduction is the main means for heat transfer in solids. So we talked about certain metals that had more thermal conductivity than others, like silver, copper, aluminum. That's probably why you see copper pans all over the place. They're really good at conducting heat. Convection involves mixing fluid molecules at different temperature. Fluid forms include both liquids and gases, so this form applies to both of them. The air is heated in one location and then moved to another. So in respiratory care, there's equipment like incubators, heated nebulizers, heated humidifiers, things like that require convection. Next is radiation. So radiant heat transfer occurs without physical contact. So when you look at the sun warming the earth, or neonates, they use radiant heat warmers to keep babies warm in the hospital. And the radiant heat is mainly in the infrared range, so it's invisible to the human eye. So now let's talk about the last one, evaporation and condensation. So evaporation, a good way to think about evaporation, how heat transfer happens during evaporation, is when you look at a dog. When it's hot out, they pant. So they stick their tongue out, breathe hard, and the moisture on the tongue turns into water vapor, so it evaporates. And heat energy is needed to turn a liquid into a gas. So heat is removed from the dog's tongue in the process. So that's heat transfer through evaporation. Condensation is the opposite. So when we were looking at the dog, that's a hot thing. You know, the dog's tongue, he's panting, it's hot, water's evaporating. So now we could think of something cold, like something we've all seen a million times is a glass of like cold ice water or lemonade. So when you have a cold object like that, the temperature wants to reach an equilibrium. So the ice will start to melt, and if you let it sit out for an hour or two, eventually it'll reach room temperature. But while heat is being transferred into the glass, the water vapor condenses. So that's how we get condensation on the edge of the glass as heat is being transferred.
Wow.
Now there's a couple more laws of thermodynamics that we should probably talk about. One of them is the principle of thermodynamic equilibrium, and that just says, given time, all systems achieve the lowest possible energy state. So if we go back to the glass of ice water analogy, basically if you let it sit for long enough, it will reach thermodynamic equilibrium. So heat is transferred into the glass until the water's room temperature. You know, everything's equaled out. And then we talked about absolute zero, the statistical law which describes the impossibilities of achieving absolute zero. So absolute zero is a theoretical level where there would be cessation of kinetic activity of a gas. So no more movement of molecules or atoms of gas. And so far scientists have gotten very close to cooling something to absolute zero, but they've never actually reached absolute zero. Let's talk about temperature scales. So we went over the three main ones that we use. There's Kelvin, Celsius, and Fahrenheit. So we need to know how to convert between those. And converting between Celsius and Kelvin and vice versa, Kelvin to Celsius, those are the easy ones. You're either adding or subtracting 273. So to convert Celsius to Kelvin, you take the Celsius temperature, say 50 degrees, and you add 273. And vice versa, if you were to convert Kelvin to Celsius, you would just subtract 273. Pretty easy. Converting Fahrenheit to Celsius and vice versa, Celsius to Fahrenheit, that's a little bit more complicated because for the most part you're going to have to use a fraction or a decimal. And there are other ways of doing it that you can find on the internet. It's kind of like personal preference. Either way, you will want to memorize whichever formula works best for you.
This is not okay. This needs to stop now. This is cancer.
I've been using the fraction one, so one of the things that I like to remember, or help me remember, is when you're converting from Fahrenheit to Celsius, you use 5/9. So I think of the three F's: from Fahrenheit, 5/9. FFF, from Fahrenheit 5. So that kind of helps me remember 5/9. And if I'm converting from Celsius, then you have to flip it 9/5. So the degrees in Fahrenheit is 9/5 times whatever you have in Celsius plus 32. So the first one was minus 32, the second one's plus 32. And like I said, that's just kind of something you gotta memorize and practice. And luckily we have worksheets. And I might make a second video on those worksheets, just kind of going through them. But for now, I think I'll just move on because it's not too crazy complicated. It's really just something that you gotta practice. There's a few more terms that we should know regarding change of state. So melting, for example, is changing from a solid to a liquid. Freezing is the opposite. That's a liquid turning to a solid. I found an interesting molecular dynamics simulation. This kind of shows what's happening to water molecules as they freeze. So we were talking about how the colder things get, molecules start to slow down. So here's a simulation of water molecules, moving around freely in a liquid state, and then as it gets colder, they start to slow down and stick together, kind of bond into these nice little patterns. And of course they still kind of wiggle around a little bit, but they're not free flowing. They've now turned into a solid. And then as ice melts, the opposite happens. They start to flow around more and more until they actually break free from each other and can now move freely again.
Just stop!
Yeah, I get it. You're getting bored. But guess what? I got news for you. The video's over. I'll catch you next time.